I think we are good to go. A very good evening to all. I am Reina, Secretary VIE SB SJCET. I am indeed pleasure to welcome you all to the webinar on Grid Modernization, Technological Advancement Beyond Smart Grid, hosted by Power and Energy Society chapter of IEEE SB SJCET. We are extremely honored and privileged to welcome our speaker of the day, Mr. John D. McDonald, the former president of IEEE PES and Smart Grid Business Development Leader for GE's Grid Solution Business. He holds an MBA in Finance from University of California, Berkeley, and BSCE and MSCE in Power Engineering degree from Purdue University. Also, our honorable speaker is an IEEE leader whose remarkable career spans over 49 years. He had published 150 plus papers, articles, and co-authorized 5 books and has also won US patent. He was also awarded IEEE Millennium Medal, IEEE PES Meritorious Service Award, and also an Outstanding Electrical and Computer Engineering Award, and many more. It's so good to have you here, sir. We are proud to get the right speaker for our session. Thank you so much for joining us. Now, I would like to invite Dr. Arun P., Branch Counselor, to formally render the welcome nod. I welcome you, sir.
Hello, Reena, am I audible?
Yes, sir, yes.
Good morning, good afternoon, good evening, ladies and gentlemen, wherever you are in the world. Once again, do I welcome you all to St. Joseph's College of Engineering and Technology, Pala IEEE Student Branch Online Web Conclave. At the outset, I would like to congratulate and highly appreciate all the volunteers and executive members for the well thought out planning and excellent coordination. I also thank the college management and Dean IEEE for proper advices, permissions, and support to organize such spectacular programs in SJCET. So far, throughout this COVID pandemic, we have been through a series of tech talks and events which molded the audience as well as the host to a great extent. And today, we are virtually gathered to attend a technical conclave on grid modernization, technological advancements beyond smart grid. Let me now move on to the duty of bidding you all a genial welcome. As you get older and think about your life experiences, you recognize certain events that were life-changing, that influenced the rest of your life. This is the first statement given in the LinkedIn page about info of the resource person of the day, Professor John McDonald. He is an award-winning industry leader, technical expert, educator, and speaker who currently serves as the Smart Grid Business Development Leader for GE Power's Grid Solution Business, who has more than 47 years of experience in the electric utility transmission and distribution industry. As Reina pointed out, he has received his Bachelor of Science in Electrical Engineering and Master of Science in Electrical Engineering degrees from Purdue University and an MBA degree from University of California, Berkeley. He is also a live fellow of IEEE. He has served as the past president of the IEEE Power and Energy Society, finance committee chair of the Smart Energy Consumer Collaborative Board, the vice president for technical activities for the US National Committee, and the past chair of the IEEE Power and Energy Society Substations Committee. The following are few of the awards he has received, such as very prestigious IEEE Millennium Medal, the IEEE Power and Energy Society Excellence in Power Distribution Engineering Award, the IEEE PS Substations Committee Distinguished Service Award, the IEEE PS Meritorious Service Award, and many more. It would be my greatest privilege and honor to welcome Sir to the session. Welcome, sir. Nextly, I welcome our principal, Dr. J. David, who stays with us not by talks, but by action. Welcome, sir. I also welcome our manager, Reverend Father Matthew Koramgura, who guides us both spiritually as well as academically. I would also like to welcome Dr. Madhukumaras, the Vice Principal of SJCET, as well as the Dean of our SB, who constantly pushes us to deliver in better ways on whatever activity is conducted in IEEE SB SJCET level. I would also like to welcome Professor P.V. Varki, Professor Emeritus and UG Dean, IEEE SB SJCET Pala. Sir always encourages any activity with learning for the benefit of the student community. I also welcome Professor Shabrinath Ji, the Vice Chair, YPSCT, IEEE India Council, whose presence always creates the sense of integrity with the section as well. I would like to welcome the chapter advisors of all the society chapters who concern the corporation makes student strive for more. Now to welcome all the participants who took out time and energy to be part of this webinar. I welcome you all to this webinar. I sincerely hope that you all have some takeaway from this webinar that you could fruitfully use for securing your future. And now over to you, Professor John, and floor is all yours. Stay safe, stay home, stay strong. Thank you all.
Okay, before we begin, I would like to remind our audience that we shall have an interactive section at the end of the talk. If you have any questions or doubts, please do drop it in the comment section. Without further delay, I would like to invite Mr. John for today's session. Over to you, sir.
Thank you very much. Want to thank Arun. Thank you very much. Ryan, Raina, thank you very much. And particularly Hannah, who reached out to me on LinkedIn, you know, and coordinated all the details with me for the talk today. I really appreciate the opportunity to talk with all of you. What I want to do is really introduce to you a lot of what's going on, not today, not tomorrow, but in the future with respect to smart grid and a lot of the new technologies that we need and we need to develop. And so it's really going to be futuristic. And a lot of this will be very important to you with research, with your studies, and you know, your future work when you graduate. So let me share my screen, and I'll bring up my PowerPoint slides. Okay. Just want to make sure. Can you see my slide?
Yes, sir.
Yes, sir.
Okay, good. So, thank you for the introduction. So, grid modernization, we've actually changed from using the term smart grid to the term grid modernization, which I like much better. You know, I've been working is in the introduction, as you said, 47 years full-time basically in smart grid. And this is my 50th year in IEEE, my 50th year as an active IEEE member. Okay, so you can see I've been adding intelligence to the grid for really almost 50 years. So smart grid is not new, right? I actually, and I'm going to show you a slide in a minute, I call it the smarter grid. And the question is, you know, what have we been doing previously and what are we doing today? So grid modernization, I like it because it's actionable. You know, we're modernizing the grid. And we'll talk about technological advancements. So we'll talk about technology, but beyond smart grid. In other words, for the future. Okay. Now, one thing I want to talk to you about here before we get into the technical material is how important IEEE PES is to you. I joined IEEE as a second-year engineering student at Purdue University 50 years ago. And I can't tell you how much I've benefited from active involvement in 3 ways. Okay, I understand the technology. I have a broader perspective and a deeper perspective of the technology because of all my participation in IEEE PS, giving talks, teaching courses, just talking with other industry experts around the world. Secondly, I've expanded my network of key industry contacts and friends. You know, on LinkedIn now I have over 14,000 connections, and it keeps growing every day. And these are you know, friends who are very interested in what I'm doing, and we exchange information on a daily basis, and that's how we all learn. Third is leadership opportunities. IEEE is a volunteer organization. There's no limit to what you can do. Okay, go ahead, volunteer for leadership positions. The more you put into something, the more you benefit from it, the more you get out of it. Okay, and you can see I've had many leadership positions: Substations committee within PES president, IEEE board of directors as Division 7 director, IEEE Standards Association board of governors. I'm currently a director on the IEEE Foundation, and I run all the technical activities for the US for CIGRE. And I've been a distinguished lecturer since 1999 for PES. My very first distinguished lecture in India was in 2003 in New Delhi at Jamia Millia Islamia University when I gave a 2-day course. And then I went to Pune and gave a 1-day course in Pune. But I've given many courses in Bangalore, Mumbai, Pune, New Delhi, and spent vacation time in Udaipur, okay, all since 2003. So one thing I want to emphasize here, again, one last point before we get into technical material. Don't spend all of your time on your studies. You know, you need a balance in your life, and you really need to take good care of yourself in terms of eating healthy and getting regular exercise. I work out with a personal trainer, done that for 10 years. Lower right photo, he was a professional American football player in the United States. We work out 5 mornings a week. I run, you know, 5K races regularly, and I'll be 70 years old in December. But age is just a number, right? It's how the energy you have, how you feel, both physically and mentally, okay? And in the upper right is my son, who Georgia Tech electrical engineer, just got his MBA at Duke University. And the morning after his graduation, he and I ran a 5K race on the Duke University campus called the Al Bueller Trail. So studies, doing well with work and doing well with studies is good, but you need to have a balance. And that's my point. You really want to have a balanced life. I've been married 41 years, have 2 children and 2 grandchildren. So these are the points I want to cover. And we'll have, you know, let's if you have questions, let me know. I'm going to also reference, I've co-authored 5 books, have many papers and articles. I'm going to reference those. And if you want copies of any of those, you can connect with me on LinkedIn and ask me, or maybe ask Hannah, who I've been talking to on LinkedIn and coordinating with, and Hannah can let me know, and I can send those to you. Okay, I'd be happy to share with you things that I talk about that I've written. All right, so let's get into key industry societal trends. This is very important. I mentioned having a good balance. It's not only good with your life in terms of work, health, exercise, and family, but also with respect to your studies and work and outside activities. And what I mean by outside activities is if you were 100% internally focused, you would go to the, you know, do all your studies with the university and that's it. Or if you were working full time, do your job and then come home, right? If you have a balance, you not only do your studies in your work, but you also get involved in groups like IEEE PES. That's always been very important to me because, as I said, that's where I learn what's happening in the world around me. And the reason I start my talk with this is if we don't know what's happening in the world around us, we may be making decisions for our research project or for our courses at the university or for our companies with full-time work that may not be the best decisions because we don't know what's happening in the world around us. So some key trends are we're transitioning from devices and systems to holistic solutions. Two very important words here, holistic solutions. A device is a microprocessor-based device with two-way communications capability, like a protective relay in a substation, or a monitoring and diagnostic device on a transformer. A system would be like a SCADA system, supervisory control and data acquisition, an EMS for generation transmission, a DMS for distribution. We'll talk about DMS in a minute. So holistic solutions, what do we mean by that? When I teach at a university, I emphasize to students, don't just think about the component, the device, the microprocessor-based device, but remember that device has two-way communications, and it can be a node in a bigger network. And the more value to the customer is the holistic solution. So always think of the bigger picture, okay? Always think of the bigger picture. And I'll show you examples of 6 holistic solutions in a minute. Holistic means organization-wide, company-wide, not just for the protection group, not just for the planning group, not just for the maintenance group, but break the silos down between the groups and do it company-wide, holistic. And a solution is a set of technology components integrated together to successfully interoperate to meet the business needs of the customer, okay? So it's very important to do things holistically, and it's very important to see the big picture. Success is a 3-legged stool, okay? If you have a stool with 3 legs and one leg is weak or it's missing and you try to sit down, you won't be successful, right? You'll fall over. So these are the 3 legs here of success are technology, industry standards, and policy. I'm going to talk more about standards at the end of my talk. Policy is the strongest, most effective driver to incentivize the customer, to cause the customer to spend money on my technology. Policy is a very strong driver, okay? When there's very strong tax incentives, for instance, to encourage people to buy electric vehicles, sales increase dramatically. When that tax incentive goes away, sales drop to almost zero, okay? Policy is very, very strong. We're also looking at, with respect to the grid, our goal is flexibility, self-healing, and being able to reconfigure. I will show you in a minute logic that we can put on the distribution part of the grid, where when a fault occurs, we can detect the fault, locate the fault, isolate the fault, and restore service upstream and downstream of the faulted segment within 1 to 2 minutes, all with no human involved, okay? So it's truly self-healing, okay? We also are emphasizing resiliency of the grid, resiliency. When we design and develop equipment for the grid, we focus on reliability, okay, and redundancy, right? But when the grid is stressed, could be stressed with extreme weather event, maybe a very strong monsoon, right? There's some kind of weather event as an example. When the grid is stressed, how well the grid withstands that stress is how resilient it is, okay? In other words, how many outages are there? How many people are without electricity, for how long? That's a measure of the resiliency. We're going to talk a little bit later about big data and analytics, but the other thing is, automation systems today have a lot of cloud components, public cloud components. So we're using the cloud to a greater extent, and we're encouraging electric utilities to interact with their customers with social media. The preference of customers is not to interact with the utility with telephone, but with social media. And for instance, I wrote an article probably 7 or 8 years ago on how we can use social media to accelerate the restoration of electricity after an outage, okay? And what I did was I said, rather than the utility having my phone number in my customer record, put my Twitter handle. You know, I'm very active on LinkedIn, very active on Twitter, and also very active on Facebook for family and personal use. But I would prefer to send outage information, to communicate with my utility through Twitter, and they can put through tweets, and they can put my Twitter handle in my customer record. So when they receive a tweet from me, they can bring up my customer record and they know my home address. Okay. And then what's very important is convergence of IT and OT to support enterprise data management. IT is the information technology part of the utility, and OT is the operations side of the utility. Okay. If we don't have this convergence, we have a disconnect in the enterprise, and we're not able to truly do enterprise data management. We'll talk more about that because it's very important. So let's look at smart grid concepts, and I want to emphasize again the convergence of IT and OT. Okay, and this is part of a cardinal rule, a principle that I have, is that before we think about smart grid, we need to make sure we have a strong grid. Okay, strong grid before smart grid. Strong grid means a robust communications infrastructure and a seamless working together of IT and OT convergence. So we have true enterprise data management, and we have a communications infrastructure that has the performance that will support all the new things we want to add to the grid, which is the smart grid. Okay, so strong grid before smart grid. You need to have a strong foundation before you start building on top of that foundation, right? So this is an important part of what we should be doing. And you know, some of the benefits are improving the reliability, the operational performance, the productivity, increases in energy efficiencies, decreases in carbon emissions, so it helps the environment. We're empowering consumers to manage their energy use and save money without compromising their lifestyle. You know, with intelligent thermostats, with more integration with smartphones and the GPS in the smartphones, with things like Alexa. You know, Alexa, turn the lights off in the kitchen of the house, and Alexa turns the lights off. And also the last point is optimize renewable energy integration. So we want broader penetration of renewables like solar and wind. And we have more focus on the distribution system today, which is very important because for many years, it was primarily generation and transmission that were invested in and not distribution. So I mentioned the smarter grid, and you can imagine, you know, it was probably 12, 13, 14 years ago when in the industry, we started talking about smart grid. And I said, wait a minute, you know, I've been adding intelligence to the grid with my work and with IEEE for, you know, almost 50 years. This isn't, the smart grid stuff isn't new. You know, let's recognize the fact that we've been adding intelligence to the grid for a long, long time. So my question is, okay, what will we be doing that's new? And so I put this slide together, and you can see in light green here is what we're doing new, and shaded in gray is the old grid, what we were doing, what we have been doing, and light green is the smart grid additions. So I could spend, you know, just a day on this slide going over things in detail, but I'll just highlight a few things. You can see voltage control here is shaded halfway. Voltage is directly proportional to load. So if it's a summer peaking utility and they're beginning to get close to their previous peak and they don't want to exceed their previous peak, we can lower the secondary voltage on the feeders and lower the load. Voltage is directly proportional to load. And so the gray part of this is doing voltage control by itself and also doing reactive power control by itself, right? VARs is losses, and we want to minimize the losses. We want a unity power factor. So what is it that's light green? Well, what's light green here is that we've integrated voltage control with reactive power control. So we call that VOLVAR optimization or integrated VOLVAR control. And that's the new thing that we're doing today. You know, we're spending a lot of time on integrating renewables into the grid. On distribution, we have to lower the losses, reduce the losses, and we call that free up hosting capacity on the feeders. So we need to free up hosting capacity so we can add more renewables, more distributed generation on the distribution system. You can see sensors here is shaded halfway. You know, we've been adding sensors to the grid for a long, long time. What's new though is a lot of specialized sensors and adding sensors to the distribution part of the grid. The one I show here is a device that I would take the oil in the main tank of the transformer and bring it through this sensor, and it could detect dissolved gases in the oil of the transformer. We have sensors where we can detect up to 9 different gases in the dissolved in the, it's called DGA, dissolved gas analysis. This is very important because if I see a specific gas in that oil, I know exactly the failure mode that's occurring in that transformer. And if I look at the rate of change of that gas, how fast it's being created, that's how quickly I need to act, okay? How quickly that transformer is deteriorating, okay? So this is what we call monitoring and diagnostics today, M&D, and then we call that asset optimization, which I'll talk about in a minute. We'll also talk about a little later is distribution management, a distribution management system. We'll also talk about, this is distribution automation. So here we're downstream of the substation, and this is where we do the VOLVAR optimization, or we do the fault detection, isolation, restoration on the distribution feeders. Then we'll talk about smart meters. We get a lot more information from smart meters than just generate the bill, okay? So I mentioned the term holistic solution, and I said I'd give you 6 examples. Here they are. So the first is asset optimization. You know, and what's really exciting today is the journey to digital transformation for electric utilities. And part of this is asset optimization. For many, many years, we were reactive, right? We waited for something to fail, and then we responded. Well, by the time we responded, you know, the transformer had already exploded, the substation was already ruined, you know, and the question would be, can we be smarter about this? Instead of waiting for something to fail, let's be more proactive. I don't want to be reactive. I want to be proactive, you know? So we've moved up the journey to digital transformation from reactive to predictive today. And we say, what health information do we need about that asset? And what analytics do we need to determine the risk of that asset? You know, what is the health of that asset? Okay. And in fact, utilities have what they calculate, what they call an asset health index, AHI, which is taking all the health information and calculating the risk of the asset. So we started with transformers because they're the most expensive, most, you know, very critical asset. And then we've moved now to high voltage and medium voltage circuit breakers. Okay. This is probably the second strongest business case today of any of these 6 holistic solutions. Now, what I'm going to show you on the next slide, I'm going to describe these in a high level, but I'll show you on the next slide what I talked about, that a solution is a set of technology components integrated together to successfully interoperate to meet the business needs of the customer. I will show you all the components around an electric utility enterprise for each of these 6 solutions, and you'll see how they cover the entire enterprise of the utility, all the components that are needed. That's why we really want to focus on the big picture today, not the component, but the big picture, the holistic solution. Demand optimization is aggregated load, but we use this as a dispatch tool today in the control center for generation transmission. When load increases and frequency drops on the grid, instead of ramping generating units, we can pull the trigger on aggregated load right? Lower the load that way, system frequency comes up, and many times it's more economic than controlling generators. We're putting in smart meters and two-way communications with the smart meters. We're investing in the distribution system. And I'm going to spend a lot of time in my talk on this because this is the strongest business case today of any of these 6 solutions. For years, we did not invest in distribution. And there's so many opportunities today. And for every dollar I invest in distribution optimization, I'm getting $5 to $6 back. So the benefit to cost ratio is very strong, 5 to 6 to 1. Okay. And you'll see examples of this throughout my talk. Transmission optimization is, one of the focus areas here today, and some of you may be working on this yourselves, is phaser measurement units, we call synchrophasers, and making better use of the phaser measurement unit information. Instead of using data that's every 2 seconds or 4 seconds, what we call SCADA data, PMUs can provide 40 to 50 samples per second. When you have that much more granularity or that much more detail about the behavior of the grid, you have a lot more insight into what's happening. So the question is, how can we use that to a greater extent? Okay. And then workforce and engineering design optimization. It's important to think about the workforce, in addition to an aging infrastructure, we also have an aging workforce. When I became IEEE PS president in 2006, the average age of the PES member was over 50 years old, and the average age of the IEEE member was 42. So we had to do, I said, we have to do something here to encourage young people to join the Power and Energy Society. And in 2008, we officially changed the name of PES from Power Engineering Society to Power and Energy Society. So the E became energy. And we focused on, helping society, helping the environment through wind and solar and distributed generation. And since then, we've grown dramatically. We were the 3rd largest society of 39 in IEEE. We're now the 2nd largest society in IEEE with over 40,000 members worldwide. So what we did was we surveyed a number of 3rd and 4th year engineering students, and we said, what are the 3 most important things to you with your first full-time job when you graduate from the university? Number 1, I want a job where I'm helping society. Number 2, I want a job where I'm helping the environment. Number 3, how much money I make and where I live. So they're very different. When I graduated with my master's degree and started my MBA, it was how much money I was going to make and where I was going to live only. So we changed the name of the society in 2008, and it's made a big difference. The other thing is, in many countries, for instance, in the United States, in the next 5 years, 40% of the employees and 60% of the executives will retire in the energy industry. And that's why we have mentoring programs, because what we do, what an experienced person does, is the art of engineering. Now, as a student, you read the books, you take the courses, and you know the science real well. But there's a big difference between science and art. You read the book, know the science, but then you need to start working with experienced people who really know how to apply that science in the real world. And that experience you can't get out of books, and you can't get overnight. It takes an investment in time. And when senior people retire, they take that art with them, okay? And that's why we have so many mentoring programs today. In the IEEE PS Long Range Planning Committee, we have 4 subcommittees, and for 2.5 years, I chaired Subcommittee 3. And in January of this year, I started a pilot mentoring program in IEEE PES, okay? We have a very strong one at GE. I mentor many young people at both at GE and outside GE. So it's very important to transfer that art, that experience, to students and young professionals, okay? So here's the technology roadmap for those 6 solutions. And, the upper left is the office and control center, lower left is the substation, lower middle is the distribution feeders. And let's just take a look at distribution with the light blue boxes. Look at all the technology components that are part of this holistic solution, from software applications in the upper left to systems, the DMS and the outage management system, the OMS, substations. We have distributed applications at the substation level. We have additional microprocessor-based devices, lower middle switches and breakers we need on distribution feeders to support the logic for fault detection, isolation, restoration, and VOLVAR devices, cap banks, voltage regulators to support the logic of integrated VOLVAR control. Now, what's challenging is these are all from different vendors, but they all have to be able to communicate successfully interoperate, which means they have to comply to the same industry standard or standards. And I'm going to finish this talk with emphasis on standards, okay? Now, there's 5 key components that need to be invested in by an electric utility. Smart meters is 1. The two-way metering communications is 2, automated metering infrastructure, the geographic information system, the outage management system, and the distribution management system. Now, for smart meters, in addition to the meter readings, we also ping certain meters at the ends of certain feeders to get the voltage. Because when we do VOLVAR optimization, we flatten the voltage profile and we lower it. But we want to make sure that the voltage at the customer at the end of the feeder is above the minimum. Every country has a standard with respect to the voltage that needs to be at the customer's premise, customer's home or factory. In the United States, it's 120 volts plus or minus 5%. So the lowest is 114 volts. And so we need to make sure and monitor what that voltage is at the ends of certain long feeders. And also each microprocessor-based smart meter has a capacitor in it. And when the meter is energized, that capacitor has enough, it's charged. And then if there's an outage, it has enough energy in it for one last communication to the utility. It says, hey, I just have an outage now, and this is the time it occurred. And that information goes to the outage management system. The geographic information system is the reference system for the network model. We make sure that gets into the outage management and distribution management systems. We take all the status changes from the distribution management system and make sure those are sent to outage management. For instance, if a feeder breaker trips, opens up, outage management has a network model and it knows all the customers that are fed from that feeder. So it now knows all the customers that are without electricity, that have an outage, from just one piece of information. And then I mentioned customers. We want to move from using a phone to interact with the utility to using social media. So one thing that's very important today is microgrids and distributed generation. And if you think about the design of the distribution part of the grid, on the bottom of the slide here, it's true that distribution controls and protection, in the design of those, we took advantage of and designed them for electricity flowing in one direction only, okay? Which was fine until distributed generation. And now when we integrate distributed generation on the grid, it causes two-way electricity flow. So the challenge today, we say at the top of the slide here, is two-way power flow and voltage regulation concerns. So we can integrate distributed generation at the transmission level, the distribution level, and the end user level. And the next couple slides, I'll talk about the distribution level and the end user level, okay? So some of the challenges we have at the distribution level, we could have an open circuit over voltage due to unintentional islanding, say of a microgrid. Also, protection ratings may not match fault currents. Why? Because when you do a protection study, to be able to set the relays, first you have to do a short circuit study. You have to know the magnitude of the fault currents at wherever the relay is located on the grid. And we typically, in our short circuit study, we typically assume a source side contribution to the fault only. right? Because distribution traditionally had electricity flowing only in one direction from source to load. Now we start integrating distributed generation, and now we have, as the penetration of distributed generation grows, we have a load side contribution to the fault. And what's even more complicating is the load side contribution varies because of the intermittency of the distributed generation, right? The sun isn't shining all the time. The wind isn't blowing all the time. So we have varying fault currents due to distributed generation. And then in a minute, I'll give you a specific example about the stress on voltage regulation equipment. So this is a microgrid project at GE that we did in British Columbia, and initially British Columbia, Canada. And initially, the focus of microgrids was in 3 applications: utility or university campuses for better energy use across the campus, military bases, and rural villages, right? And this microgrid was for Bella Coola, which is a rural village in British Columbia, not near any utility, okay? So you can see they have hydrogen fuel cells, some PV panels, photovoltaic panels for solar generation, low head hydro generation, and their base generation is diesel, which is typical. Problem with diesel is it's very expensive to transport the fuel to a rural village. Also, when it operates, it pollutes the atmosphere. So we took a microprocessor-based relay and added logic to it to be a microgrid controller. And the objective here was, let's make maximum use of the fuel cells, the PV panels, and the hydro generation, minimize the use of diesel, but make sure we satisfy the industrial and residential load continuously. And these blue boxes here at every location are all high-speed communication boxes, so we know exactly what's happening every second. Okay. Now, how do we deal with the intermittency of distributed generation? As I said, with the sun and the wind. Well, we have energy storage, right? We call that bridging storage because it may bridge the intermittency with respect to like helping with system frequency. But we also have now fast start, fast responding thermal generation, typically natural gas fired. So, you know, if it's a longer term need, then we need something like thermal generation because the batteries may lose their charge over time, right? So the other thing we've done is a couple of years ago at GE, we announced a package of 10 megawatts of lithium-ion batteries and a 50 megawatt natural gas-fired turbine generator integrated together into what we call the electronic gas hybrid turbine with software that optimizes that that integrated mix. Okay, and that's ideal because it can handle instantaneous needs with frequency with the energy storage, but it can also handle longer term needs with the turbine generator. Okay, now this is a good example of why we need to break the silos down, both at universities and in the workplace. We really need the power electronics research, the power electronics students and professors to work more closely with power system. In IEEE, we have separate societies. There's PELS, Power Electronics Society, and there's PES, right, Power and Energy Society. And I wrote this article, 8 years ago? It was published 8 years ago in Power Electronics magazine. And I said, there's new applications of power electronics in the grid, okay? And it's the result of the impact of high penetration of rooftop solar PV on the distribution system. And this article is available online, so you can search Power Electronics magazine with my name, and you'll find the article. Now, this is a real distribution feeder in San Diego, the San Diego Gas and Electric, where initially there's a low online tap changer in the substation whose objective is, no matter how the secondary voltage fluctuates, you want to keep no matter how the primary voltage fluctuates, you want to keep the secondary voltage constant, right? So the more volatility there is in the primary voltage, the more times this tap changer operates. There's 16 positions in the raise direction and 16 positions in the lower direction. Each position is 0.5% change in voltage. And then there's a neutral position. So 16, 16, and 1 in the middle. But this is a mechanical device. So the more it operates, it wears out. Its lifetime decreases. Okay. Well, initially this tap changer in San Diego was operating about 5 times a day. Now, because of the policy changes in the state of California, over 35% of the homeowners put PV panels on the roof of their home. Over 35%. And these homes are along the Pacific Ocean. So in the morning, there's a very thick fog called a marine layer of fog. It's caused by the ocean, humidity in the ocean. And then as that fog burns off, all of a sudden, all these homes begin generating. And the voltage on the feeder spikes as soon as that generation starts, and it oscillates. And there's tremendous volatility in voltage and reactive power on that feeder. And this tap changer went from operating 5, maybe 10 times a day to well over 120 times per day. Its lifetime went from over 35 years to less than 2 years, So my point in this article was we need power electronic based controllers. The future grid, as we put in more renewables, distributed generation, is going to be more volatile. Mechanical controllers don't make sense anymore, okay? So the 3 examples I gave were online tap changers, low voltage dynamic grid edge controllers. These are low voltage power electronic continuous set point controllers that we're putting at the edge of the grid, and smart inverters, okay? Now, sometimes we call the distribution management system advanced distribution management system, ADMS. And because of the complexity of the distribution system with two-way electricity flow now and many more distributed generators and the intermittency of those distributed generators, we need a system to manage the complexity of the distribution system. And that's what a DMS or ADMS does. And this is the model of centralized control where you have a basic supervisor control, which means remote control and data acquisition platform. Then you have a number of applications here that optimize the operation of the distribution system. The geographic information system is the reference model, the reference for the network model. We get all the information from the substation feeder devices that come into the DMS, and then the applications use that information, decide what device control commands are needed to optimize the operation, and those are sent back out to the field, okay? Now, a DMS will typically have these applications as real-time. These will be operating all the time that the operator will use. Now, at an IEEE general meeting or a T&D meeting, myself and one other person, we typically teach a full day course on this topic, okay? It's called on distribution management systems, and we'll go through each of these applications in detail, okay? So this group of applications are more on demand for analysis. We call these advanced analytical applications. And then this group is ancillary or extra, and these are extra applications that the utility would want to add to the distribution management system, okay? Now I mentioned the journey to digital transformation, and I show at the top here digitally enabled, but you know, no utility, no organization can get there in one step. You don't have the budget money and you don't have the people resources to do that. So what we do is we work with customers, we work with utilities and say, okay, where are you today in a journey to digital transformation? Let's say they're just starting with manual control and legacy methods. So we say, okay, let's put a roadmap together to take the journey up. Every step of the way is reasonable with respect to money that's needed and people resources, but every step will give you significant benefits. So here's the first step with adding SCADA on distribution, trouble calls, and circuit reclosers on the grid. And the benefits is 28% lower customer minutes interrupted. The next step is automation and visualization with distribution automation, outage management, network visualization tools. Now 43% lower customer minutes interrupted over the base level. And then digitally enabled is network optimization and asset performance management and outage analytics, well over 50% lower customer minutes interrupted. So, you know, it makes sense. You really have to take it step by step. It's a journey. Take it step by step, but just make sure that every step results in significant benefits, okay? Another thing is in adding automation is, let's say you have here's a very large utility with 856 distribution circuits, and they want to improve their reliability. Well, you know, adding automation to 856 circuits is very expensive. The question is, do we really need to do that? You know, this is why I myself want to get an MBA in finance, because I said, you know, a good engineer needs not only to understand the technology, but you need to be able to understand the business side of the technology. So let's look at the business side of this and say, how many of these circuits do we really need to spend money on? Okay, let's study this. It's a combination of technical studies and financial or business studies. So let's model this and study the circuits, and we find that only 23% of the circuits account for 71% of the total outage minutes, okay? So if we automate just 200 circuits, 23%, we're addressing almost 3/4 of all the outage minutes. Much wiser, much better use of money, okay, for that customer. Now, to get full benefit from these microprocessor-based devices, this is really important. We have to really understand that there's several types of data in a microprocessor-based device. This is an article I wrote in 2003. It's a 10-page guest editorial, and it's in IEEE Power and Energy magazine. This is the magazine that you get when you're an IEEE PES member, and it comes out every 2 months. It's one of the best magazines you can get to really understand what's happening in industry. There's 2 magazines that are the best. One is IEEE Power and Energy, and the other one is called PAC World magazine, PAC in capital letters, PAC World. PAC in the industry means protection, automation, control, PAC of the electric grid. So PAC World magazine and IEEE Power and Energy magazine. So I said, okay, there's operational data, which is the real-time status, performance, and loading of the grid. And this is what's used by the system operators in the control center. You know, current, voltage, real and reactive power, alarm information, circuit breaker open, closed. But what we aren't taking full advantage of is what I call non-operational data. This is both points and files of information. The primary user could be planning, could be maintenance, could be power quality, could be asset management. It's other than the operators. This is like a digitized waveform from a relay, sequence of events report from a relay, maintenance information like the circuit breaker contact wear indicator, which is the I²T that's sitting in the relay for the circuit breaker. Or I mentioned dissolved gas, moisture content in oil, say for a transformer, okay? So the operational data is time sequence at the scan rate of the master station and the control center. It's real time or near real time, and we use standard communication protocols. The non-operational data is points or a file, mostly historical, and we may need to use a vendor-specific proprietary format to extract the data file, okay? So you might have heard, you know, the Internet of Things, or what we call the industrial Internet of Things. We're bringing together intelligent machines with big data and analytics and connecting it with people at work, connecting people any place, any way, and any time for intelligent operation. This is really the next productivity revolution. And we're all saying, how can we leverage this, right, with our companies? and it's greater connectivity, which means greater need for communications infrastructure, but the benefits are huge. We're spending this is part of the journey of digital transformation, which I'll show you in a slide here in a minute. But you know, we're adding intelligent machines. We're really adding a lot more analytics, okay, to get more value from the data, as well as adding specialized sensors that I talked about, okay? So the existing situation in many organizations on the left here is each individual group has its own systems, its own intelligent electronic devices or microprocessor-based devices and databases, and there's no sharing, okay? For our goal on the right, and what I've done with many utilities, you know, is help them break the silos down with the groups, and let's put a federated data mart to bring together all the data sources and all the groups and have true sharing of data, so that all the operational users, these are the operators in the control center, and there's up to 25 to 30 different groups in the utility that are the non-operational users that could provide more value to the utility if they had the data that they needed, okay? On the left here, we're showing a standard architecture in a substation with slave data concentrators talking downstream to the intelligent electronic devices, and then a master data concentrator. And on the right here in cyan, or this light blue, is all the data sources in the enterprise. And on the right in green here is all the different user groups, all the businesses, all the groups in the utility, the non-operational users that have a need for additional data, and then they can provide more value to the utility, okay? And this is the journey to digital transformation. So this is a slide where you really want to print this and put it up in your office, right? Or in your, where you do your homework at home, let's say. Because this is what's exciting here, is this journey. I said we started with reactive, we went to responsive. Today we're at predictive, okay? So we're condition-based instead of time-based or reactive-based. We're condition-based. You know, only maintain something that needs maintenance. You know, so but predictive is only halfway up the journey. What's really cool about this is with artificial intelligence and machine learning, we can eventually get to autonomous. Now, a bunch of us wrote a book a couple of years ago called Big Data Application in Power Systems. And that we talk about artificial intelligence, machine learning, and the concept of the digital twin. I wrote the very first chapter in a book called A Holistic Approach to Becoming a Data-Driven Utility. Holistic means organization-wide, and everything is becoming data-driven today. That's why we're hiring data scientists, and electric utilities are hiring data scientists. So let me talk about standards here. I chaired a group of 25 industry experts for 5 years, and we were in charge of all the smart grid standards for the United States. We developed this smart grid conceptual reference model here. The group I chaired was called the Smart Grid Interoperability Panel. But the real thing that we needed to do was, there's about over 100 IEEE standards in smart grid. There's over 100 IEC standards. Way too many for anybody to be able to figure out, you know, what standard do I need for the work I'm doing. So we took all those standards, went through them, and we said these are really the 16 foundational standards for smart grid. Smart grid landscape is turbine to toaster, power plant to your home, and everything in between. Generation, transmission, distribution, you know, end customer. These 16 standards cover that entire landscape. Now, again, a number of us, we wrote a book. The second edition of our book on smart grids came out a couple of years ago. It's over 800 pages, very comprehensive on smart grid. It's a very, very good reference on smart grid, okay? And what's nice today is, to make standards easier, is there's one worldwide standard for control center to control center communications. There's 2 worldwide standards that are used for control center to field equipment. And really, within the field, IEC 61850 is the global standard. But in North America, both control center to field and within the field, in North America, we still use a lot of what we call DNP3 communications protocol, distributed network protocol 3, which is IEEE standard 1815. So let me finish here with, after 18 months of deploying smart grid projects, we stopped, reflected back, and we said, what lessons have we learned? And let me just highlight a few of these, and then we can have questions. So one of the things is a holistic solution is a set of technology components. You saw that with all the light blue boxes on the technology roadmap. But you know, the solution is only as mature as the least mature component. Similarly, a chain is only as strong as the weakest link in the chain, right? So what's very important with component technology is to really test the components. And we found in many cases, some of the components had to be field re-engineered or upgraded to meet the objectives. So when you put technology in the field, that's the ultimate test. You can test it in the factory, but the ultimate test is you have to put it in the field. And you expect to have some problems, and you have to be prepared for those. We also found with integration and interoperability, these are probably two of the most important words today in the industry, is integration and interoperability, is that standards are mandatory. Without standards, you're not going to be able to successfully interoperate. And then testing is important. Do as much testing in the factory as you can, much easier than in the field, but also do end-to-end testing, okay, from the device in the substation all the way up to the office or the control center. And we also found here that project management was very important. Engage one project manager for each smart grid solution. The project manager must have multi-discipline authority. So when you get out in the workplace or maybe even at school, sometimes someone will give you something to do, and they may give you the responsibility to do it, but they don't give you the authority to be successful. There's a difference between responsibility and authority. If your manager gives you responsibility but doesn't help you, give you the authority over all the groups involved in a project, you won't be successful. So smart grid covers so many different, the landscape is so big that the project manager needs multi-discipline authority to be successful, okay? And what we found here was we need to work with our customer to build an A team with their very best both project and technical members. You not only need their best engineers, but you need their best project managers. We could supply a customer the very best technology in the world. They could have the best engineers in the world, but the project could fail because of a weak project manager. Okay, that's very important. And then I'll finish with an important thing is a very new stakeholder with smart grid is the residential commercial customer. In other words, the end use customer. Now, you know, in my 47 years of full-time engineering work, my expertise is always the grid and upstream of the meter. But with the beginning of smart grid, we all found that we have a new major stakeholder, and it's the end use customer. We need to understand that customer. We need to engage with that customer, right? You can't put a smart meter on somebody's home and not engage with them and be successful. You have to engage with them. You have to manage their expectations. What new services are they getting? What's the new technology? What does that provide them? Okay, and that's very, very important. So let me finish there. Okay, and what I'll do is stop sharing my screen, and we'll go back and see. I'll stop sharing here. Okay. And we'll see if there's any, be happy to answer any questions or have any comments from folks.
Thank you so much, sir, for such an incredible session. I hope the webinar was very informative to all. Now let's move to the question and answer session. If you have any doubts or queries, please do drop it in the comment section, or you may ask directly.
Okay, here's a good question. The simplest thing about smart grid. Smart grid can be very intimidating, right? Because of the broad landscape. And I would say the simplest thing about smart grid is don't try to look at the entire landscape and figure out where to start and what to do. But the simplest thing would be find out what's most important to you. It may be asset optimization, it may be distribution optimization, it may be demand optimization. And the simplest thing would be find one part of smart grid and just focus on that first. Okay, just focus on that first. Because if you try to do too much, and this is true with your university studies, this is true with everything we do. If you try to do too much at one time, it'll be overwhelming and could be very frustrating, right? What's the most complex thing? I'll tell you what the most complex thing with smart grid is. And the reason why, as students, when you're an engineering student, I recommend that you take, as electives, take psychology courses, okay? When I was an undergraduate engineering student, 2 electives I took electives in economics, micro and macroeconomics. I took electives in French 101 and 102, but I took 2 electives in psychology. And the most complex thing with smart grid, it's not developing the technology. That's the easy part. But when you develop something new, the hardest, the most complex thing is convincing a customer to change the way they've been doing things and to adopt your new technology, okay? And what happens is, as a supplier, I'll have meetings with a customer and I'll leave the meeting and I'll look at my colleagues and I'll say, we're 2 retirements away from being successful here. 2 retirements away. There's 2 senior people there that won't change. They want to continue to do what they're doing. You need to understand the psychology of people, okay? That's why psychology is so important. The most complex thing is, it's not technology, but it's understanding people. And how do you convince a person or a group of people to adopt your new technology, which means doing things differently than what they've done before? Okay, that may surprise you. You didn't expect that. You expected probably a technology thing, but dealing with people is much more complex than developing technology. Okay. Good, very, very good question. Don't be shy. You know, if you're thinking of something, let me know. Oh, smart grid. Well, cybersecurity is very important. I mean, very, very important. I have a slide that shows a flow chart of a product development lifecycle. And from the very beginning of developing anything new today, any new technology, cybersecurity is an important part of that. I also give a separate talk on cybersecurity, and I go through every step of what happened in Ukraine a couple of years ago when hackers planned an attack over a 9-month period and then launched the attack and caused outages to 225,000 people and over 50 substations. And it's scary to see the steps that these hackers took over a 9-month period and how they planned the attack. So we've learned a lot from that. We've learned, the vulnerabilities, how to address those vulnerabilities. All of our SCADA systems today we send those to a separate, in the United States, we send them to a government laboratory, and they have professional hackers that do what we call penetration testing of the integrated system to find vulnerabilities before it's implemented in the field. So we're learning, right? And we're doing as much as we can. So smart grid, I would say that every step of smart grid and everything we do, we're doing as much as we can with respect to cybersecurity. So I would say, we're probably as secure as we can be and learning every day. Okay. Learning every day. Again, cybersecurity is a journey, not a destination. And every step of the journey, you learn something new. Good question. Cybersecurity is extremely important.
Hello, sir. Could you please comment on the recent Texas blackout that happened there? A lot of people were blaming new and renewable energy resources for that. What's your comment on that?
No, that's very timely question, because it's really not correct to blame the renewable energy. Texas east or the west Texas, the western part of the state of Texas has a lot of wind and wind energy, but the reasons really were a couple. In 2011, the state of Texas had a similar Arctic or very, very cold weather that created outages. They learned, let's say there were reports written, there was a plan developed in terms of what needed to be done to winterize the Texas grid. Okay, and that's what was important. Winterize, prepare the Texas grid for unusually cold temperatures. They suffered those in 2011. Plan was put together, but the politicians, the political leaders in the state of Texas didn't put a high enough priority on spending that money. And unfortunately, this plan was never implemented. Okay. Secondly is they had, natural gas fired power plants that were, could have operated, were continuing to operate, but because of the pipelines being frozen, they were, and a shortage of gas, they weren't able to supply gas to those power plants. Okay. So, and the other thing is the wind turbines in Texas. We have wind turbines that operate in Antarctica. They operate in very, very cold conditions. But the thing is, those wind turbines have been winterized. Okay. They have special coatings. They have special materials to operate in cold temperatures. The state of Texas didn't do that. They didn't feel it was necessary. Okay. So there's things, I'll tell you what, I talked about resiliency of the grid. We're seeing more extreme weather events today than we've ever seen in the past, right? We'll see what we call a 100-year flood, something that should only happen every 100 years. We may have a 100-year flood 3 times in 40 years, right? We're seeing many, many more extreme weather events, and we really have to plan for those. We have to spend the money to make the grid more resilient, right? For things like this. And so really bottom line is Texas had a plan in terms of what they needed to do from 2011, from what they experienced in 2011. They just didn't do it. And it happened again, right? And they suffered the consequences. So I'm hoping that this doesn't happen a third time. I'm hoping that they learn from the first 2 times and they will put a revised plan in place and actually spend the money to address what they need to do. Very, very good question. But it wasn't the wind turbines, it wasn't the distributed generation. There was a lot of other factors involved. Okay.
Thank you.
Sir, we have one more question in the comment section.
I see. It's how can we ensure that smart grid investments avoid consequences? Well, you do the best you can in, we do a lot of testing. We do a lot of testing before we get into the field. But the first question from Albin about the most complex thing. Another complex thing today is the fact that we're not just dealing with components, but we're dealing with the integration of many, many components into a holistic solution. And that makes it more complicated because there's a lot of different components all interacting with each other. And that's why we need to do a lot more testing. We can test the component by itself, but we need to test the holistic solution, right? The entire solution. And then we need to test that in the factory, okay? But we need to test it end to end, as I said. We need to test it from the device in the substation all the way to the head-end system in the office and control center, okay? We made the mistake at GE, we had smart meters, and we tested the smart meter with its communications card in the factory, and it worked fine. We went and installed the meter on people's homes. Then when we went to communicate with that meter upstream to the what we call the network management system or the head-end system, it didn't work. And we hadn't done the end-to-end testing in the factory. So we learned a lesson. Not only testing, but end-to-end testing. So how do you avoid consequences? You have to use your experience. Like for instance, for me, after 47 years of work experience, I can look at an integrated system and I can anticipate what potential consequences there'll be because of all the experience. I worked for 4 different system suppliers. I've designed systems, I've factory tested systems, I've installed systems, from 4 different suppliers for 2/3 of my career, over 30 years. So you take people like me, we can anticipate what consequences may be, and then we address those up front so they don't happen. So I think, you get very experienced people that have that insight, and then you anticipate, you address, and you do the very best you can to avoid any possible consequences. All right. Anybody else? What are my views on overcoming the limitations of converting the traditional grid system to smart grid? We've actually been pretty good with that. There's I would say 3 real situations that we have in the field. One is completely old equipment. We call legacy equipment, and we don't want to add anything to it. We'll just leave it like it is. That's a situation of just legacy, so the traditional grid, and it'll stay that way. The other extreme is completely new situation. We're building something new, so it'll have all new equipment, right? We call that a greenfield situation. Greenfield meaning brand new. But 80–90% of the time we have a hybrid situation, which is a combination of legacy and new, and they need to coexist. They need to work well together. And this is what Vincent is asking about, is converting or like legacy to smart or to new, or keeping the legacy and adding to it, right? You may not replace it, you may just add to it. And so we've gotten very good, because most of the situations we have are hybrid situations of legacy and new. So we have to do a couple things. We have to make sure that the old equipment continues to operate with full functionality, right? We don't want to adversely affect the old equipment by connecting it to new equipment. We also want to make sure the new equipment operates with full functionality too, right? When we connect the new equipment to the old equipment, we don't want to lose some of the functionality of the new equipment, okay? And so when I got involved with the Substations Committee myself in 1987 and became a working group chair in 88. and then chaired the entire substations committee in 2001 and 2. So I had 500 substation experts around the world. We're all writing the standards for substations. And when we write standards, we have to make sure that we're backward compatible. Okay, and that's how we overcome these limitations. When we write a standard for something new, we have to make sure that it will work with the existing equipment. That's called backward compatible. Okay, you can't write a new standard and only focus on new equipment. You can't do that, because in the real world, you're not going to just have new equipment by itself, right? You're going to have the coexistence of new with existing. So that's my view, is that we're doing a good job with that, coexisting of traditional with smart grid or with new, and industry standards. Our industry standards that we write support that. Good question. I wrote an article for a trade publication on this subject, a hybrid situation of legacy working well with old, because it's an important topic.
Thank you so much all. I hope the question and answer session was very informative. The feedback form link will be in the chat box. Please do fill it. Everyone, please do fill it. Now I cordially invite Hannah Susan Matthew, Chairperson PES SB SJCET, to propose the vote of thanks.
Hello, Reina, am I audible?
Yes.
Yes.
Okay, so good evening all. Myself, Hannah Susan Matthew, Chairperson, IEEE SB SJCET. So it's my pleasure to propose the vote of thanks. So I take this opportunity to thank our chief guest, Mr. John D. McDonald, for accepting our invitation and for giving us such an amazing and informative session. Thank you so much, sir. So as a token of our love and respect, we would like to present you with a virtual memento. Sir, please.
Yeah, thank you, Hannah. I can see it.
Okay, sir. So once again, thank you so much for your cooperation. So next, I would like to thank our principal, Dr. J. David, Vice Principal, Dr. Mathukumar, sir, Arun, sir, Branch Counselor of IEEE SB SJCET, Jordan, sir, PS Advisor of IEEE SB SJCET, then Professor P.V. Varki, sir, then Anuprad, sir, and all other faculties of our college. Then I would like to thank our EXICO members of IEEE SB SJCET for your constant support. Finally, I would like to thank all the participants for your presence and cooperation. So once again, thank you all. Thank you so much.
Thank you so much, Hannah Susan Matthew. So with that, we have come to an end of this session. I would like to express my sincere gratitude on the behalf of IEEE PES Power and Energy Society Chapter SB SJCET, and also to the wonderful audience. Thank you so much for being a part of today's session. Once again, thank you all. Thank you so much for joining us. Thank you.
Thank you, sir.
Thank you, sir. Bye,
Thank
sir.
you very much. Bye-bye.
Thank you, sir. Thank you once again.
Dennis, can you please send me the link for the feedback section? Dennis.
It's in the chat box. You can fill it.
But I am not using computer now, so chat box is not available. Okay, thank you, Arun, sir. Hannah, can you please forward me in the WhatsApp group?
Yes, Nitin. Yes, Nitin. I will.